So, welcome. New year, different situation. Last year, I did not expect we get in such a situation again, and but here we are. The university decided we need to leave the classroom and go into the virtual classroom and sorry, I just need to follow this. Yeah, last year we stopped in the middle of process management. You remember process management, and we jumped into scheduling. Scheduling was one of the key topics, one of the most relevant topics of operating systems. And yeah, good news. Bad news first. Bad news, we have many different ways of scheduling in literature, so it can be implemented in different ways, and it is implemented in several different ways. Literature knows many scheduling methods. And good news, I erased many of the popular scheduling methods. I told you last year I kicked everything out of my slides and my course material, which is bullshit or unrealistic. So yeah, bullshit, like last come first serve, because no one would ever implement this, I think. And unrealistic approaches like shortest or longest job first, or shortest or longest remaining time first. These are unrealistic because you need to understand, you need to know in advance what is the remaining CPU time of a process, and that's pretty unrealistic. So yeah, what we have remaining is quite realistic scheduling methods which are implemented in real life, actually. So if we look into practice, if we look into already existing operating systems, I usually prefer Linux as example, and Linux is a very good example for a modern operating system here, because it implements many different scheduling methods at the same time, and every process in a Linux operating system instance, it's always assigned to exactly one process category, or to a specific scheduling method. These process categories always implement one scheduling method, and we have several here for real-time processes. Real-time, it's not truly real-time, yeah? It's not hard real-time operation which can be implemented here. It's always soft real-time operation mode. And yeah, so we have three categories here. We have the scheduling FIFO method category, sorry, not method category. We have a round robin category, and we have a deadline category. And so here we can see it implements different sorts of scheduling, and it also implements the two different sorts of, is it preemptive or non-preemptive? In German ist es unterbrechend oder nicht unterbrechend. So it decides if a process has the CPU or a CPU core assigned, can it keep the CPU core for as long as it wants, or will it get the CPU core removed? So, and finally we have the group or the category of normal processes. So that's the usual processes we have all the time. So non-real-time processes, and that's called here the other category. And the other category implements also a scheduling method, definitely. And over the decades, we had some different implementations here. So in older times, 2 decades ago, Linux implemented a multi-level feedback scheduling. We will look what this means in a few minutes. And later it implemented the O of 1 scheduler for a few years. And the most recent implementation here is that's the completely fair scheduler, and that's state of the art in Linux. And we will have a look how this works. So if you want to learn about a specific process on your running Linux system, what sort of scheduling policy is it assigned to, and what's the priority, so you can check with the command line tool checkrt, and so here you can learn about a specific process ID, you learn about the policy and the priority. And if you want to modify this, so if you want to assign a process to a different scheduling policy, so you can do this with the same command line tool here, and you specify just the policy. So let's have a look into the single scheduling methods I want to show you. The first one is priority-driven scheduling, and that's a pretty simple thing. In real life, you have seen this. The processes have a priority value assigned, that's state of the art, and the next process that gets a CPU core assigned to, it's the one with the highest priority value. And the priority value, it may depend on many different criteria, like a static priority value, or the number of resources it needs, user importance, rank of a user, real-time demands, and so on. So in principle, such a scheduling method can be implemented in a preemptive and in a non-preemptive way, and the priority values, say, can be static or dynamic. So in a static way, it's not very flexible, so the values are kept over the time, and in a dynamic way, so they are adjusted, probably because how the processes behave. If they are kind and give back a CPU core after some time on a voluntary basis, or if they always use their full time slice duration, so processes can be leveled up and down. And this approach, this scheduling approach, it's called multi-level feedback scheduling, and we will discuss this later in this slide set. So static priority-driven scheduling has a big drawback in regard of fairness. If we have processes with a lower static priority value, it may happen that these processes starve, which means they will not get the CPU core at any time, so they are they will never be able to be executed. Dynamic multi-level feedback scheduling, that's a pretty common thing, and the static implementation is more common for real-time applications. Just to sum this slide up, priority-driven scheduling is pretty common, and it's state-of-the-art for interactive systems at all. If we want to investigate the implementation or how such a scheduling method can be implemented, we have one explanation here from Stellings, which is pretty good. It's a very simple approach. So we have several waiting queues here, and one waiting queue for every priority level which is implemented now, and processes that are created, they are assigned to the correct waiting queue which matches the priority level. And so the waiting queues have different time multiplexes, and so they get the CPU for different amounts of times. Yeah, it's about the length of the time slices. And so if a process has access to a CPU core, so it can be executed until termination or until the time slice has expired, and so the process gets the CPU core assigned, and maybe it's blocked, and so it's in the waiting queue for blocked processes, and if not, so it gets attached to a waiting queue or inserted into a waiting queue again. So that's a pretty straightforward thing, and it's not so far away from the implementation of many operating systems. Yeah, it's not so. It's a bit macro perspective, not micro perspective. Yeah. So if we talk about scheduling methods, it's always important that we can compare scheduling methods with each other, and for comparison we always need a scenario, and so we need to be able to execute different scheduling algorithms for a given scenario, and so we can compare the results and we can specify this or that scheduling method is best for this given scenario now. So, and in our example here, in our scenario, we have 4 processes, and for the sake of simplicity, we expect a single CPU system here now, which has only a single CPU core. So quite outdated, do you think? Probably, and yes, that's true, but so we just keep it simple. At the same point in time, time point 0 here, the processes are available, which means they are in state ready, they are in the idle waiting queue, and now we have these 4 processes with static priority values, and so we can show the execution order by using a timeline, by using a Gantt diagram. And so if it's just non-preemptive here, all processes were available at the same point in time, and so we can see process B had the highest priority level, followed by C, followed by D, followed by A, and so that's the execution order we have. CPU time, which is the time a process needs to be executed on the CPU until termination. These times we had them in front of. Yeah, it's just for the example. Pretty unrealistic, but we needed this. So we have our execution order here, And now we are able to calculate the runtime of every process and the average runtime of all processes, and we can calculate the waiting time and the average waiting time of all processes. Runtime is the time from the moment when a process existed, when it came into the idle waiting queue, until the moment when it terminated. So it's basically the lifetime of a process. It's the CPU time plus the waiting time. So it's the time the process had access to a CPU core and the time the process waited for a CPU core. So, and the waiting time, yes, that's just the time when a process waited for a CPU core. It's the runtime or lifetime minus the CPU time. So it's the lifetime minus the time where it did run. So, and in our example here, we can see process A terminated at after 32 milliseconds, process B after 4 milliseconds, C after 11, and D after 24. All processes emerged at time point 0, and so that's our runtimes, and the waiting time is the runtime minus the CPU time. And so we can read it here, but we can also calculate it here. Runtime minus CPU time is waiting time. And so by summing this up and by a division with the number of processes, we get the average values. Pretty simple thing, but always keep in mind these values can tell us something about efficiency or not so efficiency, but it's always focused on a given scenario. So that's our example now for priority-driven scheduling. What do we have next? You remember our list here, we started here. Our next record here is first come, first serve, and in the scheduling topic it's popular to call it this way, but you can also just call it FIFO, because first come, first serve it operates according to the FIFO principle. Sorry. So the running processes, they are not interrupted in FIFO, so it's a non-preemptive scheduling. It's a fair scheduling method because processes cannot starve, and the average waiting time, it may be pretty long, because maybe you remember that from the last moments of our last class we had before Christmas. So I told you the execution order of processes, it has a big impact on the system performance. If we go back in time, so it was this slide basically, and so we can see if we execute short running processes before long running processes, so the runtime and the waiting time of the long running processes it gets just a little bit worse. But if we modify the execution order, so if we have long running processes before short running processes, the average performance gets pretty worse, and that's exactly what we have here. If you remember the first week of class, so I told you about batch processing, a very old-fashioned way of operating system um, of a group of operating systems and a working principle. And yeah, FIFO, or first come first serve, that's a scheduling method which is pretty useful here for batch processing. And as I told you a few moments before, FIFO is also implemented, for instance, by Linux for non-preemptive real-time processes. So that's the scheduling policy, or that's the scheduling category for the most relevant, for the most important real-time processes in a Linux operating system, if you have such processes. Yeah? So it's a common way, if you have such a very important process, to assign it to a specific CPU core and make it a FIFO non-preemptive real-time process, and so it will run without any interruption from the operating system side. Yeah, so I have no idea if the hardware is so much failure safe, so this depends on the scenario again. So yeah, and again we can have our example. Yeah, we have again our 4 processes on the old-fashioned single core, single CPU system, and we now have as slightly modification here, we don't have priority values now, we have different creation times. And just to get rid of any discussion now which process is executed next. And so at time point 0 we just have process A in the idle waiting queue, and so it's executed next. And when the other processes arrive in the idle queue, we have no interruption here because it's non-preemptive, so A is executed until it terminates, and next we have the execution order according to the position, to the single positions in the idle waiting queue. And so here we have next B, C, and D, and again we can calculate the run times and waiting times. And now it gets a little bit more fishy, because now we need to think about the different creation times. Yeah, D, for instance, terminates at time point 32, but it did not arrive before time point 5, and so we have 32 minus 5, it's 27, for instance. Yeah, or here C terminated at time point 19, it arrived at time point 3, 19 minus 3 is 16, and so on. And the run times minus the CPU times, that's the waiting times. And so here again we have our average run times and waiting times. And if we it's pretty stupid now to compare this with our priority driven scenario, because there we had priority values we did take into consideration, and here we just ignore them. But yeah, it's just a simple example. Yeah, our next algorithm on the list is also pretty straightforward. It's round robin. Round robin is something you have seen probably several times during your education, during your studies, maybe also in school. Round robin is quite close to FIFO, because in round robin we operate with time slices. In German it has a really old-fashioned name, Zeitscheiben, maybe not so common anymore in literature. Yeah, and the time slices, they have a fixed duration, so processes are organized in a cyclic waiting queue, and it's organized according to the FIFO principle. And if a process got access to a CPU core, it can utilize the entire time slice, and at latest the next process in the cyclic queue gets the CPU core assigned next. It's a fair working principle. We have no starving processes here. If we compare round robin with FIFO, round robin is just FIFO but with time slice duration unlimited or infinite. So maybe you remember winter is not good for me. Sorry. So maybe you remember we discussed before Christmas context switching. And you remember context switching processes are switched back and forth because we always have more processes than we have CPU cores. And if a process gets a CPU core assigned, the already running process needs to be kicked away and the state of the process needs to be saved, needs to be rescued. And that's done by the operating system by using the process control block. So if we think about different time slice durations, so time slice duration has a strong influence on the overhead of our operating system, of our scheduling, and it also has a strong influence in the way how the system feels or how it feels using it, interacting with it. Because if we reduce the time slice duration, so we have more process switching, and so we have an increased overhead, so we will waste more CPU resources. And if we increase the time slice duration, so the system will not feel very responsive. The user experience will be not very good. The system will feel like it hangs a bit. So typical time slice duration or time slice duration values, it's in the millisecond range, single or double digit millisecond range. Round robin is pretty well suited for interactive systems, and for instance in Linux it's used for real-time processes that are preemptive, that can be interrupted. So the round robin is definitely a preemptive scheduling method. That's the only difference compared to FIFO, and it's pretty good for processes that have a short execution time, and so that's definitely the case for interactive systems, because most processes here are not long-running processes. So again, we do our tiny example scenario, and now it's at first glimpse it's pretty simple because we just ignore any priority values, and we also ignore now any times where processes emerge in the idle waiting queue. So it's the same for processes, basically. It's the same machine, and now we need a time quantum, a time slice duration, and so I decided 1 millisecond. That's the most simple thing. And so the Gantt diagram looks pretty horrible. Horrible if you need to draw it, maybe in an exam situation. Obviously that's not a good idea to have something like this in an exam, and that's the reason why I think I never did round robin in a written exam, because if you have one mistake, everything is ugly again. And if you make it more complicated with different start times or whatever, so it gets even more ugly. And yeah, I remember I had one time in my life I did a exercise question, I think, with time quantum 2 milliseconds, and people got pretty nervous and complained a lot. So yeah, so it's nevertheless it's straightforward. It's the same working principle, but now we have a process switch every millisecond, and so after here time point 14 process B has finished, and after time point 24 process C has finished, time point 26 process A has finished, and process D is the final one here and terminates at after 32 milliseconds. So yeah, again here we have our calculation, and the results here are pretty worse now, yeah, because yeah, the scenario is just the way it is, but we can see the processes, even the shorter ones like as process B, they need to run for a pretty long time here. Yeah, so we can organize the execution order by taking into consideration the order when the processes arrived, yeah, like in FIFO, or we can yeah, and also in round robin, or we can take care about priority values, but we also have the freedom, or operating systems have the freedom to calculate the execution order because of the deadline. Yeah, processes can have a deadline assigned, and if the deadline expires but the process has not terminated, maybe the result will be pretty ugly. So in real-time operation, working with deadlines is pretty common. Yeah, definitely now we need a deadline assigned to the processes that are scheduled according to such a policy. It can be done in real-time operating systems, and even in Linux, yeah, we have a scheduling policy for earliest deadline first scheduling, and that's also for preemptive real-time processes. Yeah, this can be implemented in preemptive and non-preemptive way. In a preemptive way, it's often seen in real-time operating systems, as mentioned before, and if we talk about non-preemptive operation, so it's probably useful for batch processing and so, but yeah. Again, our example scenario, it's the same for processes, and now we have deadlines, and the deadlines decide which process is executed next. So it's basically the same like when we had the priority values, but in the reverse order. Shortest value is now what counts. And so consequently here in this example scenario, process C is executed first, process B next, process A next, and process 34 next. So and again here we have our runtimes, we have our waiting times. Please don't take it too serious in comparing these results. If you really want to compare scheduling methods, you need the same scenario for many different algorithms or policies, and so you can compare it. But here it's a bit fishy. Yeah, one scheduling method I also want to show you but honestly it's not quite popular in operating systems, but it's very popular in distributed systems. It's fair share. Fair share is a pretty interesting approach, and it's one of the youngest scheduling approaches, I think. In fair share, the scheduling system does not distribute resources between single processes at first point. So it distributes resource shares or amounts of resources to the users. So every user gets a specific amount of resources assigned depending on which user group it belongs to or so, and the users the users themselves decide how many processes do they want to execute, and the processes of a single user need to share among themselves the resource share the user got assigned. So here in our example scenarios, in the first one, here we have a resource, it's a server machine, or just any CPU, and so here we have a job queue, a waiting queue, and we can see we have two users, both got the same resource share, 50% of the overall resources, and so user 1 started 3 processes and user 2 just a single one, and we can see the single process of user 2, it has the full 50% of the resource share, and the 3 processes of user 1, they need to share the 50% among themselves the user got available. And here in the second scenario we can see the users 1 and 2 still have their 3 or 1 process executed, and but user 1 now has a schedule of 75% and user 2 a schedule of 25%, and so we have this given execution order consequently. Such scheduling implementations are pretty much state of the art in distributed systems, in cluster systems, and also in cluster systems with many sites. And the idea or the background is, motivation is, if you have a big distributed system, many thousand compute nodes maybe, or even many sites in a distributed compute cluster, you have different user groups, different users and user groups, and so maybe you have students and scientists and PhD students and university professors and researchers, and also the different institutions which are a part of this infrastructure, they invested different amounts of money, and so by using fair share you can ensure that everyone gets a specific amount of resources depending on how much money the connected institution was able and willing to pay, basically. So yeah, we are talking here about job scheduling in distributed systems and meta-scheduling. A meta-scheduler is a scheduler between sites, between data centers, basically. So now let's go to the bit more abstract scheduling methods, but we are getting closer and closer to practice, I think. So definitely the most common scheduling implementation in modern operating systems is multi-level feedback scheduling, because the motivation here is, we all have seen the single scheduling policies have benefits and drawbacks. They are not not a single one was well suited for every process. And next, we cannot predict the CPU time in advance precisely. Yes, that's also impossible. So yeah, the idea now is, or the motivation is, processes which behave well, so which are kind and give back a CPU core if they don't need it anymore, or do not always utilize their full time slice. So these are good processes, and so they get probably a little bit more resources next time because maybe they are very much interactive. And others, processes which use always full time slice and are really resource demanding or resource hungry, such processes are maybe background processes, and so they will be sanctioned. They are leveled down in the priority hierarchy. So in multi-level feedback scheduling, we have many waiting queues, and each one has a different priority or time multiplex, which means a different amount of CPU time it is able to maintain or manage. And if a process is created, so it's assigned per default to the highest priority value, to the top waiting queue, because maybe it's a really interactive one and really short running, and so it will get the CPU pretty fast. And maybe it's good after 1 or 2 CPU runs. And if the process gives back the CPU on a voluntary basis, so it will keep the priority level. It will stay in the same waiting queue. And if not, so it will be handed down to a lower priority level next time. So we have dynamic priority levels here. Definitely it's preemptive scheduling. The processes are interrupted if a time slice has expired. And here in this diagram we can see the working principle again. A new process is created, so it is inserted into the top waiting queue, and after some time it is here in first place, and it gets the CPU core assigned. And if it's a kind process, it will stay here in the same waiting queue, and if not, it will be handed down. That's a pretty interesting approach, because we don't need any estimations now for runtimes or so. All processes are treated equally, and either they behave well or either not, and so they will be handled in the explained way. This scheduling method, it's pretty good for new processes. They are preferred over long-running processes, because the longer a process runs, the more it will be handed down, and so probably it's just a background process and we don't care if it runs for a long time or not. And the interactive processes, they are hopefully they can terminate pretty fast. If we check the list of modern operating systems, we can see most modern operating systems work or implement according to this working principle. We have Mac OS and different BSD variants, which is pretty well understandable, pretty easy understandable, because Mac OS uses a free BSD kernel, but also the Windows NT family implements a multi-level feedback derivative, and also old-fashioned Linux implemented this for the non-real-time processes 2 decades ago, basically. State of the art in Linux, that's what I told you before, is the completely fair scheduler. And the completely fair scheduler works in a yeah, it's quite interesting, quite impressive, interesting working principle. I have no idea if other operating systems have implemented something like this. So here's a kernel. It maintains a so-called virtual runtime value for every normal process, for every non-real-time process, and according to this assigned virtual runtime, so the scheduling is done. So this value, it represents basically a virtual CPU runtime in nanoseconds, and so it's pretty simple to find out how long did every process have access to the CPU in the past, how long had it access to the demanded resources here. And the process with the lowest virtual runtime value gets the CPU assigned next. The processes are organized in a so-called red-black tree. That's just a self-balancing binary search tree, and such a tree is implemented for every CPU core. So we have basically a scheduling component. Here we have a tree for every core. Yeah, and the processes are inserted into this binary search tree according to their virtual runtime values. So the scheduler tries to give every process the more or less same amount of CPU time, of CPU resources, and so if we have a number of n processes, and so every process should get a round of 1 divided by n of the CPU time which exists. And if a process runs, it can run until the virtual runtime has reached the target portion which is permitted, 1 divided by n of the available CPU time. And next, if the next process gets the CPU core, so the executed CPU time gets added to the virtual runtime value. The idea or the motivation here is every process should get a fair amount of CPU resources. And these virtual runtimes here, they are the values of these keys here. They are the keys of the inner nodes, and the outer nodes, leaf nodes, they have no data and no keys. They are just called no null values or null nodes. And for fairness reasons, it's always the leftmost process in the tree which gets the CPU core next. And if a process had access to the CPU and did some calculations, so it is inserted into the tree again according to the new virtual runtime value. So it's always taking processes from the leftmost position, giving them the CPU core, and if they lose the CPU core, they are inserted somewhere here again. So it's a continuously moving or traveling from processes from the left to the right, and so it's per definition pretty fair. And yeah, simple question, what's about priority values? Even in present day Linux operating systems, you can assign static priority values to processes. That's no problem. So where is this implemented here? And the idea is the time can run at different speeds. Yeah, the virtual clock can run at different speeds. If you have a process which has a high priority, time will run slower. So effectively, the nanoseconds are squeezed. Yeah, and if a priority has a low, if a process has a low priority value, the nanoseconds are shrinked. Yeah, so the clock runs faster. So it's basically an indirect implementation here of these static priority values. Yeah, that's good enough here for a quick introduction into present-day Linux process scheduling. Here we have a summary again about our classic and present-day scheduling methods. So again, we have here the red records we decided we will not discuss because they are unrealistic and or even bullshit. Yeah. And also here I needed to erase one record, the O of 1 scheduler of Linux. Yeah, it was just popular for a few years, and it's now more than 10 years ago, I think, when it was removed by the completely fair scheduler. And the O of 1 scheduler, it's really an impressive topic. It's really cute, but it's horrible for a lecture. Yeah, because you need a full I think you need a full hour to explain it with slides, and for a dead horse technology which is not used now anymore, I don't think it's worth the resources now. So I kicked it away from the slides. So yeah, back to the track. We have discussed different scheduling methods, and we can differentiate between preemptive and non-preemptive scheduling. Some of these methods can be implemented in both ways. We have the category of fairness. Yeah, you remember fairness. No process should starve. Every process should get the CPU core assigned at some point in time. And most of the today relevant scheduling methods are definitely fair. CPU time must be known in advance. If yes, it's bullshit. It's unrealistic. If no, it can be implemented. Yeah, and so consequently, everything we mentioned here, answer is no here, so it can be implemented in real life. And take priorities into account. Yeah, in combination always. In the pure just algorithmic form, not always, but state-of-the-art scheduling systems usually take priority values into consideration, except some special applications here, like FIFO real-time policy in Linux, which is super seldom used, and yeah, just for one or two processes maybe in real life. So yes, that's good enough for scheduling. Please, do you have some questions about scheduling? Do you have some questions?
I have a small question. We were talking about scheduling, but only using one core. And what is happening if it's like many cores or core? Is that possible to see how the scheduling works, or just like
Again. I missed the first part of your question again.
We were seeing scheduling just like using only one core of the
Yes,
CPU. And it's gonna be too complicated if we just like try to see what's happening with more cores.
it's basically the same story because the kernel implements a scheduler for every core. Because every process or every thread, no matter if you want to differentiate this here now, every process or every thread is assigned to exactly one process, to exactly one core. You can influence this. Yeah, you can specify the core a process or thread is assigned to at the very beginning or during execution time. Um, but it's the same working principle
Okay.
from scheduler perspective.
Yeah, okay.
You just have many schedulers. So if we think about here the red black tree, yeah, if you have 16 cores maybe in your machine, so you have 16 schedulers started by the kernel, and you have 16 red black trees in the memory now. So it's not a big difference if you explain it with one or many cores. Is the question good? So okay.
Yes, I'm just like thinking which process are going to the different cores. That's what I'm not understanding. If I'm just like making very large process and making to the core number one and some small in the core number two and number three, but is there any schedule for different cores, or is there
There is a balancing. The modern operating systems usually implement a balancer, and if there is a strong imbalance between process assignment and CPU cores, so it's processes are shifted automatically from process cores that are probably crowded to other ones which are probably close to idle or so. There is a balancing
okay.
functionality, yes, and you can influence this behavior by specifying exactly such scheduling policies like these ones here, yeah. Maybe if you want to be sure that a really important task, a really important process has one CPU core alone. Yeah, you specify, okay, now it's scheduling policy FIFO, and so you can be sure it will not be interrupted and it will not be disturbed on its dedicated CPU core. So such influence
Yeah.
ways of influence you have.
Yeah, okay, that's clear. Thank you.
Okay. Any more questions about scheduling? If not, we can go to one of my favorite topics. But before we go to one of my favorite topics, maybe the most favorite topic, I have some news. Next week, we have a special guest. Yeah, my fine colleague Oliver Harm. He will do a guest lecture. You maybe most of you know him from computer networks class. He will tell you something about implementation, organization, and work in a big open source project which implements an operating system. It's a Riot operating system. Mr. Harm is a real expert in open source real-time operating system creation, and he will tell you some really interesting stuff, I'm sure. So I told him, and I tell you, it's exam relevant, so please take it serious. Yeah, attend the same as you do here with me, and I think it's really interesting what he has to tell us. So yeah, okay. My probably most favorite topic. Yeah, that's a good appetizer, I think. Give me a second. Here it is. Whoa, 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 go away. So now, wow, my favorite topic. Yeah, interprocess communication. So we are still in the topic of processes, process management, one of the key topics of operating systems, definitely. But inter-process communication is really, really, really relevant because processes need to interact with each other. And how is it done? How can it be done? That's very important also if you want to do software development and so. Yeah, when I'm worth my money every month, you should have gained a basic understanding at the end of the semester of what issues can happen if inter-process communication does not work well. So we are talking here about critical sections and race conditions. We will talk about 3 different categories in inter-process communication, and that's the synchronization, it's the communication, and the cooperation. So synchronization, it's basically the execution order again, but now in regard of critical sections. Communication is the way data can be exchanged. We have 4 different ways, and we have cooperation. So how can processes work with shared resources with each other? So again, we have an exercise sheet for sure, which focuses the content of this slide set. It's exercise sheet 9. And yeah, here's the highlighted, the green part here of this picture you are hopefully quite familiar with now. That's exactly what is focused here on slide set 9. I will not manage, definitely not manage to discuss slide set 9 in total today, but that's not a big issue. We will continue in 2 weeks after Oliver Harm had his event here, his special event next week. So yeah, open inter-process communication. So yeah, you all are pretty aware what processes do. Yeah, say read and write and do whatever stuff with data. But sometimes they need to call each other, or need to wait for each other, or need to coordinate a resource operation with each other. So it's just different sorts of interaction which need to be possible. And so how can it be done? It can be done in different ways. Yeah, how can data be transferred from process A to process B, and how can resources be shared among processes? So we will discuss this in this class. An often asked question, what's about threats? Threats have the same challenges and issues and also solutions in inter-process communication as we have with processes. It's just a little bit more simple because the threads of a process are already in the same address space. That's a bit of simplification, but everything else is the same. So yeah, if we talk about different processes and inter-process communication, first we need to be able to find out where do we have potential issues, yeah, where can something go wrong, and that's what we call the critical sections. In critical sections we have read and write operations on shared data, and here the operating system or the developers need to take care that we have no processing, no execution of critical sections of many different processes at the same time. Everything else which is not so critical, it's uncritical sections, and here in uncritical sections we just have read operations on shared data and no write operations. If we talk about shared memory, accessing shared memory, common data, so the operating system need to ensure mutual exclusion. In German der wechselseitige Ausschluss. So this needs to be done by the operating system, and if the operating system cannot do it or has no implementation to offer this, it's part of the job of software developers to do this. So here we have a real life example, a pretty simple example, I think. It demonstrates critical sections and what can go wrong if we have no mutual exclusion. So here we have two processes, a process X and Y, and both processes want to insert print jobs into a spooler directory. And you remember spooling we had in the first or second week of this semester. Spooling meant originally we have additional hardware to get rid of stupid I/O jobs, to free our CPU from stupid I/O jobs. Today we sometimes still have additional hardware like DMA chips, DMA processors, direct memory access, but we also have pure software implementations of spooling, like the spooling process, which takes away print jobs and printer interaction from our other processes. So we have here we have the spooler directory, and the processes want to write into this directory, and process X now asks what's the next free record in the spooler directory, and the reply is its position number 16. So now we have a process switch, a context switch. Another process gets the CPU assigned, and process Y asks the same. What's the next free record in the spooler directory? And the reply from the spooling system, from the spooling process, is still the same. It's number 16. So process Y still has access to the CPU core and stores now the print job into position number 16 and increments this value now by 1. And now again we have a process switch. Maybe the time slice has expired, and process X gets again the CPU core assigned, and process X, its state is now available again, so it continues where it was. It has been interrupted, and it now also will write its sorry.
Hello, Moto.
Oh, shut up. Not now. So, sorry. So, it will write the print job into time slot 16, and nice ringtone. Yeah, it's a standard ringtone, sorry. It will write the print job into the available position number 16 and increment it for itself. So yeah, as consequence, the print job of process Y became overwritten. Yeah, it's lost. So we have a loss of data, and that's definitely a race condition. Yeah, a race condition, that's an unintended situation, race situation between two processes. Both wanted to modify the same position, same record, and so yeah, it's bad luck. It was just because of the stupid process switching. Yeah, next time it will maybe not happen again, or maybe it will happen often now. We don't know. Such problems are pretty rough to fix, to nail down, because sometimes it goes wrong and sometimes not. So symptoms, maybe they appear, maybe they disappear for some time. If you want to get rid of this, if you want to avoid this, we have several ways implemented by operating systems how to get rid of this, and one of them, most popular one, is the semaphore concept. Yeah, we will talk about the semaphore concept again in 2 weeks maybe in this slide set, but at the end of this slide set. It's a part of the corporation of processes subtopic here. Yeah, no operating system course without the horror story of the Terrac 25, because that's the big one poster example of when a race condition killed people. Yeah, that's it. In computer science, we often think, oh, if we have bugs, it's not so bad. Yeah, what can go wrong? Nobody dies. But that's not true actually. Yeah, if you program rockets and the rockets explode in a different place, maybe many people are dead. Or if you work in healthcare system implementation, so it just can happen that people get hurt or die. And in this example here in the United States, in the 80s, the Terrac 25, it was a linear particle accelerator, something which is used to help people that have cancer. Yeah, cancer cells tumors are burned to the core, yeah, by radiation, by high energy beams, and so in the United States here some people died because of poor programming and quality assurance, and it's pretty good that it happened in the United States. Not good for the victims, but good for the world in this example, because when something like this happens in the United States, it gets pretty expensive for the people who develop these things, and so a lot of stuff is created in regard of documentation, yeah, for lawsuits and so. So such documentations, such investigations are really helpful to prevent such things, hopefully, in the future. And if you want to learn what went wrong, what sort of poor programming caused here the death of some people that got 100 times of the radiation dose, that were exposed to this 100 times radiation dose, it's very well explained, in detail explained here in this free article here from the 90s. but it's a long read. Yeah, it's more than 20 pages in the IEEE computer magazine, so it's a really it's really worth to read, but it's rough stuff actually. Just to sum it up a little bit, what went wrong in these investigations, several bugs were identified in the software, and one of these bugs was called the Texas bug because people died in Texas by this bug. And so it was just a race condition which was responsible for wrong settings between the device and the user interface console. Yeah, the user interface process was not synchronized well with the control process, and to make it worse, this issue only happened when the people who who interacted with the machine, when they had a lot of experience. So when they had a lot of experience, they were pretty quick in doing user interactions, and so the race condition happened. Probably during testing, when the engineers tried to do test protocols, and so it never happened, probably because people worked pretty slow and did not want to do anything wrong, and so, but yeah, so it happened only during routine after some years. Yeah, here we have some interesting quotes. Yeah, I just read it now here. Once the data entry phase was marked complete, the magnet setting phase began. However, if a specific sequence of edits was applied in the data entry phase during the 8-second magnet setting phase, the setting was just not applied to the machine hardware due to the value of the completion variable. The user interface would then display the wrong mode to the user, who would confirm the potentially lethal treatment. Wonderful example for a race condition. Bad for the people who became exposed to this radiation, but yeah, very interesting to read. There are many more interesting resources in the internet to learn about these things. I have some links here. But that's just a good example to show you it is important that we know what we do in life, yes, that we know how to program and that we know how to do process interaction, because otherwise maybe it can become a bit dangerous. Yeah. So yeah, inter-process communication, you have seen in the table of contents, it has 3 big subtopics. Yeah, synchronization, cooperation, communication. Yeah, and that's because inter-process communication, it has 2 aspects here. It has the functional aspect. Yeah, that's what we want to do actually. Yeah, we want to do communication, which is data exchange, data transport from one process to the other process. And we have cooperation, which means shared resource usage, yeah, like shared memory. It's common data, and so we need to handle read and write operations in ways that we have no race condition. And we have a temporal aspect. Temporal aspect, it's the time when operations are executed, and that's done, or that's followed by the synchronization. That's summed up here as synchronization, the temporal aspect. Definitely communication and cooperation both base on synchronization. So synchronization is the most elementary form here of interaction, and just because if synchronization is bad, yeah, we have wrong results probably. So, and that's the reason why the order in this slide said, the order of the subtopics is the way it is. Why we have first the synchronization subtopic, and next the communication, and finally the cooperation subtopic. So yeah, let's start with the synchronization. Yeah. So first we have the signaling. Signaling is pretty simple. It's just one way to synchronize processes, and that's just by specifying an execution order. So here we have two processes. We have X and Y, A and B. Sorry. Each process has one critical section here, X and Y, and X need to be executed before Y. So we have a signal operation, and this signal operation tells process B that process A has finished critical section X, and so process B consequently need to wait for signaling, for the signal operation of process A. We have wait and signal, and maybe process B needs to wait for some time. The implementation is pretty simple, pretty easy here. We have the signal operation, which has a signal variable, and so it sets the signal variable, and the wait operation will check is the signal variable set, and if not, it will wait. It will wait in an infinite loop for the signal variable, and if the signal variable is set by the signal operation, so wait will just reset it. That's also called busy waiting in computer science. Yeah, busy waiting adds a signal variable. The signal variable can be implemented in different ways. Yeah, for the most simple way, it can just be a local file, which is created by one process as signal operation, and the other process waits for waits for the existence of the local file. Busy waiting is pretty simple, but it's also pretty bad. It's a bad programming because you will waste a lot of CPU resources probably. It's shitty programming. The wait operation, it's an infinite loop, and so it will waste a lot of CPU resources. Yeah, all the time it checks for if the signal variable is set. It needs to occupy a core. Another process needed to be kicked away from the CPU core. State needed to be saved, rescued in the process control block, and now the wait operation is executed, and maybe for nothing, and again a process needs to be put on the CPU core. Yeah, in literature it's also called a spin lock, or it's called polling. But yeah, just try to memorize, it's really bad. If you want to do it in a better way, in a more resource saving way, it's better to block process B until process A has finished its critical section. And this can be done by a slight modification here. So we can see the signal variable here. It will set the signal operation. Sorry, it will set the signal variable, and it will check, do we have a waiting process? And if yes, the waiting process gets deblocked, and if not, we just don't care. And the wait operation will check if the signal variable is set, and if not, the process blocks itself. And so if the signal variable is set, it's reset. Yeah, the benefit definitely we will waste no CPU resources, um, but the drawback here is we only have a single process that can be in waiting state. Yeah. In literature, that's what we call the passive waiting. Yeah, here we had the active or busy waiting, and here we have the passive waiting. Um, if you want to implement this in Linux, we have, for instance, the function signal suspend. So here we can use this. So a process can block itself until it is woken up by maybe a signal like signal user 1 or signal user 2, and such signals can be sent to process IDs by using the command line tool kill. Yeah, not the finest name, but it's just the way it is. And so processes can be woken up. As alternative, we have system calls like pause and sleep, or function calls which do the same. So time is running. I think we stop here. It's 1 minute left basically. This 1 minute we use for questions. Do you have questions?
I have a very small question.
Yes.
This process interaction is nothing that it's similar to the protecting mode, because it was like seeing that it's just like this interaction between processes, like the same that you were saying that in the protecting mode it's get a little bit more secure, that not other processes they have access to the memory of the process.
You mean the protected mode in memory management. It is a different topic, but it has some boundaries which are pretty close to each other, because if we talk about shared resources like shared memory, common data, shared memory means we append a bunch of memory addresses to the address space of multiple processes. Yeah? And that's something where it connects with memory management, with virtual memory. But for the moment, I think it helps you to see it as two different topics. Yeah. So one thing was memory management. So the memory address space every process has assigned, and where it can do whatever it wants. And we have inter-process communication, which is one big topic of operating systems, and gives us different ways of how processes can work with each other, interact with each other. Okay, for the moment?
Yes, for the moment it's okay.
Okay. Some more questions? I have no idea how long this situation will be. I have no idea if we can have in 2 weeks again our room and do class in personal. I have just no idea. Please check the course webpage every few days, and on the course webpage, in the course timetable, you will also find the login credentials and the URL for the guest lecture of Oliver Harm next week. Yeah, and please attend. I think it's pretty interesting. So yeah, thank you for attending. I hope you enjoyed it a bit. It was not too boring, and we make the best of the situation. Yeah. Okay. Bye bye.
Thank
Bye.
you.